Welcome to G Fun Facts Online. Beneath our feet, the Earth's crust is in constant, silent motion. We're all familiar with the violent jolts of earthquakes, but in the last few decades, scientists have discovered a far more subtle and enigmatic form of tectonic movement, the silent earthquake. These aren't earthquakes in the way we usually think of them. They produce no shaking, no destruction, and no headlines. Instead, they are slow slip events, quiet episodes, where faults release energy equivalent to a magnitude 7 earthquake, but over days, weeks, or even years. They shift the ground by centimeters without anyone feeling a thing. First detected just over 2 decades ago, these hidden movements are forcing a profound reevaluation of how we understand geological hazards. Today, we delve into the unseen world of silent earthquakes. The cause of these quiet giants lies deep within subduction zones, the vast boundaries where one tectonic plate dives beneath another. Imagine this zone as a complex geological patchwork, not a simple, uniform boundary. Scientists broadly divide a fault into 3 distinct zones based on depth and temperature. The first is the locked zone. This is the shallowest part of the fault, less than 30 kilometers deep. Here, the plates are cold, brittle, and locked together by immense friction. Strain builds up for hundreds of years, like a colossal spring being wound tighter and tighter, destined to be released in a sudden, powerful megathrust earthquake. Deeper down, we find the stable sliding zone. Here, extreme temperatures and pressures make the rocks hot and more like putty. In this zone, the plates can slide past each other smoothly and continuously, generating no significant seismic activity. But nestled between these 2 extremes is the transition zone. Here, the conditions are just right for slow slip events to occur. The rocks aren't strong enough to stay locked, nor are they hot enough to slide continuously. This special region is the breeding ground for silent earthquakes, and it has a few key ingredients. First, the rocks themselves. The fault here isn't a smooth plain but a messy mixture of different rock types with varying strengths. Some rocks exhibit a property called velocity-strengthening friction. This means that as they start to slip faster, the resistance to that slip actually increases. This property acts as a natural brake, throttling the movement and preventing it from accelerating into a full-blown catastrophic earthquake. It promotes slow, stable sliding instead of violent rupture. The second, and perhaps most critical ingredient, is water. As an oceanic plate subducts, it carries a tremendous amount of water trapped within its rocks. At the depths of the transition zone, around 25 to 60 kilometers down, intense heat and pressure squeeze this water out. The fluids become trapped at pressures almost as great as the pressure of the overlying rock itself. This immense fluid pressure counteracts the clamping force holding the fault together. It effectively lubricates the fault, reducing friction and allowing the plates to slip past each other slowly and episodically. The third factor can be the very topography of the seafloor. Underwater mountains, known as seamounts, can get dragged into the subduction zone. As a seamount pushes into the fault, it can squeeze water out of the sediment ahead of it, making the rock more brittle and prone to locking up for a conventional earthquake. But in its wake, the seamount leaves a trail of fractured, weakened rock saturated with water, creating the perfect lubricated conditions for a slow slip event to occur. This unique combination of mixed rocks, velocity-strengthening friction, and high fluid pressure creates a state that allows for the immense release of tectonic energy in a quiet, creeping fashion. So if these events are silent and unfelt, how do we even know they're happening? Their discovery was a triumph of modern technology. Silent earthquakes don't generate the sharp, high-frequency waves that traditional seismometers are designed to detect. They are invisible to the classic tools of earthquake science. Their detection relies on measuring subtle, slow-moving changes in the Earth's surface. The primary tool is the Global Positioning System, or GPS. But this isn't the GPS in your phone. Geodetic GPS stations can track the position of a point on the Earth's surface with millimeter-level accuracy. In a subduction zone, these GPS stations normally show the land being slowly compressed and pushed by the tectonic plates. However, during a slow slip event, these stations will temporarily reverse direction, moving back as the built-up strain is gently released. Over many years, this creates a distinctive sawtooth pattern in the GPS data, revealing a cycle of slow strain accumulation and episodic release. It was this pattern, first observed in the late 1990s in the Cascadia region of North America, that provided the first definitive evidence of silent earthquakes. While traditional seismometers can't detect the slow slip itself, they are crucial for picking up its faint accomplices, non-volcanic tremor, and low-frequency earthquakes. These are weak, rumbling seismic signals that often occur at the same time and in the same location as a slow slip event. The combination of GPS data showing the slip and seismic data showing the tremor provides a powerful combined view of the process. The tremor acts like an acoustic fingerprint, helping scientists track the slow slip as it migrates deep underground. Another powerful tool is a satellite-based technique called interferometric synthetic aperture radar, or InSAR. By comparing radar images of the same area taken at different times, InSAR can create a detailed map of ground deformation over vast regions. While GPS gives precise data for specific points, InSAR offers a landscape-wide view of the subtle warping of the crust, helping to create much more detailed models of where the slip is happening. More recently, scientists have even started applying machine learning algorithms to continuous seismic data. These tools can sift through immense datasets and identify subtle statistical features in the background seismic noise that may precede a slow slip event by months, long before GPS can detect it. Perhaps the most pressing question surrounding silent earthquakes is their relationship to the planet's most destructive events, megathrust earthquakes. Do they act as a safety valve, harmlessly releasing stress? Or are they a sinister precursor, loading the dice for a catastrophe? The answer, scientists are finding, is a complex and unsettling both. Slow slip events typically happen deeper than, or adjacent to, the shallow, locked part of a fault where megathrusts are born. When a slow slip event occurs, it changes the stress in the surrounding crust. While it relieves stress in the area that slips, it can transfer that stress to the neighboring locked section, pushing it closer to its breaking point. A growing body of evidence links slow slip events to some of the most powerful earthquakes in recent history. Before the catastrophic 2011 Tohoku earthquake in Japan, scientists retrospectively identified significant slow slip activity. In the final months, migrating slow slip transients were observed creeping toward the point where the magnitude 9.0 main shock would ultimately rupture. Similarly, the 2014 Iquique earthquake in Chile, a magnitude 8.1 event, was preceded by an intense and well-documented slow slip event that started months prior and moved toward the eventual epicenter. However, the link is not a simple cause and effect. Hundreds of slow slip events have been documented around the world that were not followed by a major earthquake. A recent global analysis confirmed that while the rate of smaller earthquakes tends to increase during slow slip events, the data does not yet support a direct connection to widespread, major earthquake hazard. Silent earthquakes are not a definitive predictor, but they are a clear sign that the tectonic system is active and transferring stress. Understanding this intricate dance is paramount for improving long-term hazard forecasts. While slow slip events happen worldwide, 3 regions have become natural laboratories for studying them. The first is the Cascadia subduction zone, stretching from northern California to Vancouver Island. This is where the Juan de Fuca plate dives beneath North America, and it's famously the site where slow slip events were first discovered. The region is now synonymous with episodic tremor and slip, a recurring phenomenon where slow slip events happen with remarkable regularity, roughly every 14 months in some areas. During each event, the land shifts a few centimeters, relieving stress deep on the fault but, crucially, adding stress to the shallower, locked portion. Since the Cascadia zone hasn't produced a megathrust earthquake since the year 1700, an immense amount of strain has built up. Its regular slow-slip events provide an invaluable opportunity to study the stress-loading process on a fault known to be capable of a magnitude 9.0 event. Next, we go to the Hikurangi subduction zone off the east coast of New Zealand's North Island. This zone has become a world-renowned laboratory because it hosts the shallowest known slow-slip events on the planet, occurring just a few kilometers beneath the sea floor. Their shallow depth makes them much easier to image and study. The Hikurangi zone has a fascinating split personality. The northern part is a hotbed of frequent slow-slip activity, likely lubricated by subducting underwater mountains. The southern part, however, appears to be locked, accumulating strain for a future great earthquake. By studying the well-behaved northern section, scientists hope to understand the rules that govern the more dangerous, locked southern section. Finally, we visit the Nankai Trough in Japan, one of the most seismically hazardous regions in the world. To monitor this threat, Japan has invested in an unparalleled network of offshore observatories, with instruments drilled directly into the seabed. This network has successfully detected shallow, slow-slip events, some lasting for over a year. The data suggests these shallow events act as a tectonic shock absorber, periodically releasing strain. While this might reduce the risk of a rupture starting in the shallowest part of the fault, scientists remain concerned that the deeper, locked portion is still primed for a major earthquake. The discovery of silent earthquakes has opened a new frontier in seismology. It has revealed a spectrum of fault behavior far more complex than previously imagined, filling the gap between the geologic slowness of plate tectonics and the violent speed of an earthquake. While they do not yet offer a silver bullet for earthquake prediction, they provide an unprecedented window into the stress-loading processes that precede catastrophic ruptures. Every silent earthquake that is recorded adds another crucial piece to the puzzle. By learning to listen to the Earth's silent rumbles, scientists hope to one day better anticipate its loudest cries. Thanks for joining us on Fun Facts Online.